Okay.
Yeah.
Okay. Where did Claudio go? Ah. Let's see. Okay. I don't see any organizers. Claudio, well, I guess I'll go ahead and start. So the notes for Lecture 1 and the first part of this are actually now online on the conference website, and I would love to have comments so that the lectures improve somewhat between the current form and the final form in the Blue Book. So please do send me anything you notice that should be better. So I want to have one last little bit of mathematical background, which is just the Berry phase. And the reason why we care about the Berry phase is that it gives us gauge fields in parameter space. And for us, parameter space is going to start off as momentum in the Brillouin zone, and then it will become sort of boundary phases or boundary fluxes when we want to think about disordered or interacting systems. But either way, we're going to have some kind of gauge field. And for integer topological phases, I promise we will get to real physics and even experimental data by the second part of the lecture, not my data. Integer topological phases, you can actually give a pretty complete systematic picture in terms of the Berry phase. And along the way, you get theories of other things that are not necessarily topological, but are still geometric. And maybe the classic example is electric polarization. And the reason for spending a little bit of time on that, so this is, a quantity that people measured back in ancient Greece, places like that, but it was really theoretically understood how to compute it, at least from one unit cell, only around 1990. And the reason why, even though this is an old thing, it's worth thinking about a little bit, is that if you understand electric polarization properly, the so-called modern theory of Thouless, King-Smith, Vanderbilt, etc., then you can get pretty simply to the magnetoelectric effect and the theta angle, which will be a big subject of the next lecture. Okay, so let me do one quick calculation, and I'm going to do it just a little bit differently from how Leonid did it. So I'm going to be a tiny bit lazy in one respect and work a little harder on something else. So the respect in which I'm going to be lazy is, I'll assume that you learned the adiabatic theorem in undergrad quantum. So you do believe me if I say that if I've got a non-degenerate state that remains non-degenerate as I change the Hamiltonian, then if I change the Hamiltonian slowly, there are no transitions out of that state. So what possibly interesting thing could happen? Well, what we want to show is that, let's say I've gone from T initial to T final. What we want to show is that the final state I can write as the following. Two parts. One is the part that you would guess just from remembering how states evolve in quantum mechanics, which is, we could call it the energetic part. So this part is just how much phase do I build up. Maybe my energy is a function of time, but again, I'm just focusing on one non-degenerate level, and all the other levels are staying some finite energy away. And then the interesting part is the second part, e to the I gamma. And all of this phase multiplies what I'm going to, the initial wave function. And this is going to be for a closed loop in parameter space. So by parameter space, I mean I've got some parameters in the Hamiltonian, call them lambda sub I. This I is not initial, it just counts which parameter I'm talking about. So I've got my various knobs, and I've turned them around so that they're the same thing at the final time as they were at the initial time. So to get this, from this gamma, I need to define what gamma is. I want reference wave functions. So lambda tilde is slightly different from, psi tilde is slightly different from psi. Psi tilde is just a function of the lambdas. These are my so-called reference wave functions. So what I mean by that is, let's say that before I do my time evolution, I figured out, okay, these are my possible parameters. I've diagonalized the Hamiltonian at each value of parameters. I've figured out which is the state that's evolving adiabatically from my initial state, and I've chosen my phase to define this wave function, and that's basically arbitrary, except I want it to vary smoothly. So the assumption, which we should think about at the end, because it's actually not true in the most interesting cases, is that there is a smooth choice of psi tilde of the lambda I for all lambda I. So let's assume for the moment that I could just choose smooth reference wave functions everywhere, and in general this is true only locally. And we'll see examples of that. In fact, the existence of non-zero Chern numbers is related to the fact that there are always local smooth choices, but not always global smooth choices. And that's true if there's some non-trivial topology. Yes?
What do you mean by reference wave function?
I guess what I mean is this is not the wave function as a function of time. So the key point is that by the time I get to lambda of t, so the parameters will have some values at t. This is equal to some phase, which is really what I want to compute, times the reference wave function at the lambdas at that time. So maybe a way to put it is, suppose I had my spin in a magnetic field. That would be, the Hamiltonian is minus n hat dot s. Let's say before I did the evolution, I've chosen my favorite spinor basis for the wave function of the lower eigenstate of this. That's my reference. And then when I evolve, by the time I've gotten to there, when I'm solving the Schrödinger equation, I'm guaranteed to have, in a sense, the same physical state because it's non-degenerate, but I don't know what the phase will be compared to my reference phase. So in our simple case of one non-degenerate state, the only difference between the actual state and the reference state as a phase, it would be a little bit more complicated. If we had a degenerate set, which is what we will be thinking about for non-abelian Berry phases, like in topological insulators, then this would just be somehow expanded on the basis. If the basis is just one state, then the expansion is just a phase by normalization. So did that make sense? Okay. So the reference wave functions are something I kind of fix ahead of time, and there's certainly a choice in that. So I should check at the end of the day that all the physics doesn't depend on how I chose the phases of my reference wave functions. So this gamma, the Berry phase, is now the integral over the path of the following object defined from the reference wave functions. So in shorthand, we write this as integral of A, which is going to be my very vector potential that we'll come back to. And let's make these vectors if you want. And now this is a closed loop in parameter space. Okay, so I should show later on that this is indeed like a vector potential. It has a form of gauge invariance and all that. But for now, let's say this is some quantity that I'm claiming is the phase I build up when I do this evolution. So looking at this statement, this whole thing is e to the I theta. So in other words, theta, the total phase I've built up, I'm claiming has an energetic part and a Berry phase part. And once we've set up all this notation, it's pretty simple to show that. Just maybe 2 lines. So from what I've said, psi twiddle, the reference wave function at lambda I, inner product with psi at t, where I'm not writing it, but these are the parameters that the system has gotten to at time t, so I guess if I want to, I could do that. This thing, that's e to the I theta of t, that combination. If I take the time derivative of the left-hand side, okay, well, time acts in slightly different ways on the right-hand side. So we know from the Schrödinger equation, the Schrödinger equation applies to my wave function as a function of time. That's h psi, which is e, whatever e was at that point in parameter space, so e of lambda I of t psi. And then there's a second part, which is how is this changing? So the time derivative of the bra here, that time derivative is only coming through the fact that these parameters are changing in time. So that gives me a d lambda I dt dot partial lambda I of the ket. Okay, so combining these two, I get a pretty simple expression. This is just a gradient. You mean this thing? Or no, just gradient with respect to parameters of the wave function. That's what gives me the connection. So A is what I mean by connection. But yes, I did make this assumption of smoothness. Okay, so combining these two to take the total derivative with respect to time of that, let's write it this way. So what I really care about is dt theta. So that's going to be dt of e to the I theta times minus I e to the minus I theta. So what I did there was just figure, when I take the derivative of this, I'll get dt theta times I times e to the I theta, and this is just to cancel out the stuff I don't want. So that dt e to the I theta, well, that's the time derivative of the left-hand side So combining two, I've got to take this thing and on the left-hand side put a psi twiddle. I can pull out E in front since that's just a numerical factor. So let me stick this minus I in front. And then I've got a minus I E of t over h bar psi twiddle of lambda. So that came from where the time derivative is acting on the second. I'm going to write my psi in a minute, but from the first part, from when the derivative acts on the first part, I've also got a plus d This all has a psi of t on the right. So that came from the time derivative of e to the I theta. I've already pulled out the minus I. So the last thing I've got is e to the minus I theta. E to the I theta was psi twiddle psi. So e to the minus I theta is psi twiddle. So this thing all multiplies psi of t psi twiddle of lambda. And now, the nice thing is that here I've got psi t. That's the projection operator onto the one-dimensional subspace spanned by psi. But this wave function lives in that subspace, which means that these two cancel. In other words, that projection operator, once I've got this on the right side, is just 1. And I'm left with my desired result, because this and that give me the identity. So that gives me an minus I times minus I gives me a minus 1, a minus e of t over h bar. And then I've got the Berry phase part, which is the total derivative with respect to t. Well, let's write it out first. dt of, let's write it this way, grad lambda psi twiddle. And note that this thing, because of the normalization of psi twiddle, this is pure imaginary. If I flip it, I get a minus sign. But this is exactly the time derivative of what I wrote down before for the total phase, where this is the energetic part, and this is the total time derivative of A. So then, integrating for phi of t, I get the integral of minus I e of t over h bar dt plus gamma, the Berry phase. Sorry with the minus. I think maybe I want the I in the denominator. Anyway. Okay, so that's my notion of Berry phase, but now we got this thing A. That's my Berry vector potential. So let's think about that a bit more and note that it has a nice property. So the Berry part, we said that gamma was integral psi twiddle line integral in parameter space. So let's do a little experiment to say, well, suppose that we'd chosen a slightly different set of reference wave functions. How would this change? So suppose now psi twiddle is some e to the I. If I want to make a U1 phase change, I've got some scalar function of parameter space, let's say. So I've got two reference wave function choices that differ by this U1. Let's plug that in. Then what I'll get is almost what I had before. So let's just think about A. How does this vector potential change? Well, I've got one term where this derivative just acts on psi 0. So I've got e to the I chi psi 0, grad lambda, e to the I chi psi 0. I'm going to have two terms, one where this derivative acts just on psi 0, which is going to be easy because this e to the I chi will cancel out the e to the minus I chi I get from this once I put it in the middle. So I'll get what I had before, but I'll get a new term. The new term is coming from when the gradient acts on the phase factor. So if I make that change, then A is now I psi 0 grad lambda psi 0 plus a new part. Well, that new part, I'll have an I times this I in front, so that's a minus 1. And then I've got psi 0, the gradient acted on chi, psi 0, but now this is just a number, so I can erase the wave functions. Or in other words, I've got A I had before minus the gradient of the phase, and this should look familiar. This is exactly the same U1 gauge transformation you've seen before in electrodynamics. So that's saying that in this case there was a U1. In general, if we had repeated the same derivation with an n-fold set of degenerate states, then we'd get UN gauge fields by the same argument if n degenerate states. And someone asked before if there's any use of the non-abelian part in metals. I don't know of one, but there's a nice use of the non-abelian part in insulators, which is this magnetoelectric effect. But for today, let's mostly think about the abelian case. Okay, so that's the Berry phase. And now, enough math. What does this Berry phase object really mean? So let me try to give A, the physical intuition, and then B, how is this connected to all that fancy cohomology stuff? So physical intuition 1 is kind of in general. The Berry A is a gauge field in parameter space. So that's always true. And number 2, okay, let's get a bit more specific. So far, this has just been about a general parameter space. What if we were thinking about electrons in the Brillouin zone? For the case so I'm going to assume you know Bloch's theorem. In a periodic potential, we can write my wave functions as a product of a plane wave and a part that has the real space periodicity of the unit cell. If I define my Berry vector potential in K space from the U's, then what this is really about is actually the spatial position of the electron. And I'm going to try to make that more precise. Or, let's say, spatial position of the electron inside the unit cell. So note that as a trivial case, if I just had one atom in the unit cell in a tight binding model, the Berry phase is automatically 0. To get a non-trivial Berry phase, in particular a non-trivial F, or a Berry connection that is not gaugeable to 0, I need to have the wave function evolve non-trivially, not just a phase that is, but actually change as a function of the momentum. And that can't happen if I've always just got a one-dimensional Hilbert space. So already we're making some assumption that our crystal is a tiny bit non-trivial. It's got at least 2 orbitals in the unit cell. And if that's true, then here's why maybe people should have realized a long time ago that there had to be this anomalous velocity term in the semi-classical equations that Leonid wrote down. So let me give you a picture for why there is that term, and then to get back to more topological and precise stuff, I'll tell you about electrical polarization. Okay, so the semi-classical equations of motion there's the Lorentz part. So that is, there's an electric part and a magnetic part in how the crystal momentum evolves in time. And then there is one term here that's in Ashcroft and Mermin, and one term that isn't. And it might be, on some level, the most important thing left out of Ashcroft and Mermin. I don't know. So there's one part, which is the group velocity. We know that when we put an electron in the crystal, the energy-momentum relation is modified, and that modifies the velocity. But you probably know from studying waves and all that, this would be true even if there was no structure inside the unit cell. This is just a general property of waves. So the second part, well, the way it's often written is something like k dot cross f, where f is curl of A. Sorry, I'm not going to be very strict about writing vector signs. So why is this here? Well, think about this as the following. This is dki dt. Okay, so there's an... and then here, this f is dA how to put this? J dki. If I'm looking at dxj dt. So there's a part in the velocity in one direction that's related to how is k changing and how is A changing with k. The way to think about what's going on here is the following. Suppose I had a unit cell with 2 pieces, A, or 2 atoms, A and B, and maybe at some point, K1, the electron is mostly sitting on A. And then at some K1 plus dk, at a slightly different block momentum, the wave function is more localized over here. So in other words, the wave function has moved within the unit cell if I change k. Well, if it's moving within the unit cell as k changes, and if k is changing in time, then as a result of moving in time, I should see an extra velocity because, on average, the electrons have moved a bit within the unit cell. So that's what this term means. But for that to make sense, it must be that A sub j has something to do with position in the j direction. And let's make that a bit more precise and then say a bit about what does this all have to do with topology, and then we can show some slides and talk about the integer quantum Hall effect. So to make that precise, let me give you a formula and then tell you how it's derived. I won't go through the details. But I think if you were going to ignore the history and do things in maybe logical order, this would have been the first thing to be discovered, because it's kind of the simplest. So we know from electromagnetism that we should be careful about things that are observable shouldn't depend on the gauge. So what are observable things? We can make from A. Well, historically, the first was the following statement. And that's the following. And this is TK and N. So TK and N were doing Berry phases at about the same time as Berry. They just didn't know they were called Berry phases. But Berry was the one who really recognized how general this concept is across physics. They wrote the following formula, that sigma xy in a two-dimensional system in a magnetic field, and the magnetic field should be commensurate with the unit cell, so I still have a Bloch's theorem. Then there's an E squared over H, and then this multiplies, let me write it this way, sum over I, n sub I, where n of sub I are the Chern numbers, and I'm only going to sum over occupied bands. And the Chern number, so we're going to say what this is in a more mathematical language in a second, but operationally, you can compute it as the integral over the two-dimensional Brillouin zone, which is a two-dimensional torus of the curl of A, or F. So in a two-dimensional system, there's just one non-trivial component of F. You can think of it as Fz. So dxay minus dyax, and I believe that the way things are normally normalized, there's a 1 over 2 pi there. And this is specifically the Berry curvature derived from the Bloch wave function in band I. So they derived this by writing down the Kubo formula and doing a lot of massaging, but it kind of obscures this fact that Thouless was maybe the first to realize a couple of years later that the Berry phase really is about where the electron is sitting, and there's an even more fundamental or simpler formula than this one, but you have to think a bit because it's not as obvious that it's really quantized. So this is something we'll come back to in a second, but this is a topological invariant. It's an integer. It's the Chern number of each band. If I bring two bands together so that they touch, then their Chern numbers add, so there is kind of a group notion. And it's physical. This is what I can measure as long as I'm in a gap. So I've got either completely filled bands that contribute or completely empty bands that don't. As Leonid flashed up, there's probably, I think most people believe, including me, that there is a contribution to the Hall effect in metals if I have a partially filled band, which is just the integral of this over the part of the band that's filled. That's not topological because I'm not integrating over all of T2, but it is there physically. But what's maybe even more basic, and let's just go down to one dimension.
Question?
Yes?
So you said something about the magnetic field not messing up the fluidity of the lattice, but even if you have a constant field, the potential of like X, Y.
Well, I'll make a supercell. So to be precise, if I have commensurate flux, let me do a Hofstadter problem. So think about a square lattice. And actually, this is a good example. I probably should have discussed this even without the question. So let's say I want to put a magnetic field on this. And if I gave you an arbitrary magnetic field, let's see where the problem happens. So let me choose a gauge. So before I put on the magnetic field, let's say I've got hopping matrix elements that are T. So you probably know how to solve the tight binding model on the square lattice. Let's say you want to make your life more interesting. You want to have a flux of phi in each unit cell. So So then, well, one way to do that would be to have, let's say this bond is now T e to the I phi. So all my vertical bonds are going to be T, but my horizontal bonds, which are my AX vector potential, those are going to change. So all of these are T e to the I phi. All of these are T e to the 2I phi. And all of these are T e to the 3I phi. So, okay, that looks like a problem because it looks like there's no longer a unit cell. But there is a unit cell if phi is of the form, so 2 pi in the units I'm using would be like one flux quantum, where p and q are in the integers. So if I've got a rational multiple of a flux quantum, then if I go up q steps in the vertical direction, I can make a supercell. So let's make our lives simple and take q equal to 3.
What are the phase vectors? Or how do you get ETN?
Well, if you want to put a magnetic field in a lattice model, like a tight binding model, the constraint should be that if I move an electron around, I should pick up an Aronoff-Bohm phase that's equal to the flux through that. So if I move around this unit cell, I've picked up a flux phi. So that's, I guess, how you put a magnetic field in a tight binding model. You could derive it from minimal substitution if you wanted. Okay. So in other words, we've put...
How does this relate to a continuum case where you would put it in by substituting p with q minus qa?
Well, so the normal continuum, you get Landau levels and so on if you take the limit of q very large. So if you like, you'll probably be hearing about Chern insulators and stuff like that. A Chern insulator is a lattice model of the integer quantum Hall effect. It's sort of, so, okay, going back to the history, before TKNN, people understood the integer quantum Hall effect and kind of the continuum picture with Landau levels and all that, and that's nice, and 2-degs are really in that continuum limit. If I ask about what is the flux through one gallium arsenide unit cell, it's tiny, infinitesimal almost. But there is a quantum Hall effect, and this is much closer to what happens with topological insulator Simpson orbit coupling. There's no reason why you have to be in the continuum limit. You can get a quantum Hall effect in a tight binding model like the Hofstadter problem. And that's what we're doing now. But yeah, so if you want, why is there a phase here? Well, the reason is that I should get, in addition to the hopping I had before, there should be an E times I integral of A dl. So I've put in an AX on the horizontal bonds. So if I've got an AX that is linearly proportional to Y, that's the Landau gauge. That's a constant magnetic field. If you thought about the electrons as spatially localized at the points of the lattice and tried to put in a magnetic field whenever an electron moves, there is a gauge choice. I could just as well have chosen the vertical bonds, or if I wanted to do a lot of work, I could try to make something like rotational gauge on the lattice. The only requirement is that when I go around a circle, the total phase I pick up should be the flux through the circle. And now, the reason for requiring periodicity, or a rational multiple of the flux quantum, is that if I do that, I can then define a larger unit cell, because if phi was 2 pi over 3, then by the time I get up to here, this is equal to t again if phi was 2 pi over 3. So in other words, then I've got a new unit cell which is 3 times bigger than the original unit cell. So if I make the real space unit cell 3 times bigger, that makes the first Brillouin zone 3 times smaller, which means that there are actually 3 bands, even though I started with 1 band and now I've got 3. So that's good because I said I needed more than 1 to get a non-trivial Berry phase. And you might ask, well, suppose I did this calculation, what would these topological integers be for... So I haven't proven that the Chern number is an integer or anything like that, but let's just... Suppose I did this example and I computed... well, let me draw the band structure first, and let me draw a cut along one direction because the full E of kx, ky is beyond my ability to draw. So if I did this in zero field, I'd have something like that out to pi over a, and minus pi over A. So what I've done now is kind of make this smaller by a factor of 3. I guess I should really make this y, fun. And now, once I turn on the magnetic field, I actually will get gaps between the bands. And they probably don't look exactly like that, so don't take the energy literally. But if I compute the Chern numbers, I'll get 1 minus 2, 1 in this problem. If I took 5 instead of 3, I would get 1, 1, minus 4, 1, 1, as it happens. So those are the Chern numbers of the Hofstadter problem. And what that should mean, and what you can do as kind of a numerical experiment, even, although I need to talk about pumping for how you would do this, if you filled up the first one and left these empty and measured the Hall effect of your crystal, you will get a quantum Hall state. So in other words, we haven't put in any disorder yet. Real samples, of course, have disorder, but we have broken translational invariance by putting on a lattice, and as a result, I get an integer quantum Hall effect that's nice and quantized. So let me now go on with polarization and then come back to the question of maybe why intuitively should this Chern number A be quantized and B be related to the location of the electron. Any questions about this? Or that's good. Okay. All right. So a formula that's probably being used by someone computing a real material right now is that polarization well, to get normally you'd think to get a non-zero value, I should break inversion symmetry. Put a question mark next to that. If I gave you one unit cell, so if I gave you a big chunk of material, you'd measure polarization by looking at the surface and saying how much charge density is there per area. If I gave you a unit cell, if people did not realize, it's kind of amazing until 1990, how, if you're given a unit cell in the block states, how do you compute the polarization? And the answer is surprisingly simple. So let's take, suppose for simplicity we had 2 bands. Let's say we've got UC conduction, empty, and UV valence full. So 1D insulator with 2 bands, to keep life simple. Then let me write down a Berry phase formula for the polarization and tell you how it's derived, and I promise that in the notes I will derive it. So the get the number right. Polarization is charge times integral decay of the Berry vector potential from the occupied band so this is A, it's not F. And then again, there's a 1 over 2 pi. So remember, the Brillouin zone is periodic, and that's actually important here. Decay of A over 2 pi. And if I went up in higher dimensions, I get the same thing. So this is the formula that people use if you want to know how polarized is your crystal of some ferroelectric or whatever. Let's check that the units are right. So here, in 1 dimension, this just gives me something with units of charge. In higher dimensions, I've now got ddk, but I've still got A. There's some E times some number. So if I want to know the polarization in the I direction, I take the vector potential in that direction. So now this has extra factors of k. So for example, in 3D, d equal to 3, this has units of charge per area, which are actually the right units of polarization once you remember that the polarization is either dipole moment per volume or surface charge per area. So, okay, well, we should check. From what I've just told you before, you should be very nervous anytime you see a physical quantity that's not in terms of F, but is in terms of A. And the reason for why I mentioned polarization is there are really at least two fundamental kinds of objects that appear in the type of topological phase I'm talking about now. So forget about the fractional quantum Hall effect for the moment. There's a type which is like the Chern number. It's an integral of a gauge invariant quantity. And those are tied actually to even dimensions. And then there are objects that appear in odd dimensions, which were only understood. So the idea of the Chern form, the even dimensional objects were understood by Chern in kind of the late 40s. The odd dimensional objects are in general called Chern-Simons forms. And those were only understood in the 70s. But this is actually this is the Chern-Simons form in 1D. It's almost kind of trivial. Let's check one physical property about it to see if it makes sense, which is what happens under a gauge transformation. Because this is really to illustrate the difference between the sort of odd dimensional quantities and even dimensional quantities that we'll see later on. So we've got, well, A goes to A minus grad chi. Let's stick in one dimension, so everything's easy. Well, that's a gradient with respect to k. We know that for my gauge transformation to make sense, it should satisfy that the integral of the change in the phase over the one-dimensional torus, that is the one-dimensional Brillouin zone, this should be a multiple of 2 pi. In other words, I can make a gauge transformation, so n not equal to 0 is sometimes called a non-trivial or non-null homotopic gauge transformation. Because basically, so our gauge transformations are a phase, but that phase has wound as I went around the Brillouin zone one time. So I'm allowed to do that. What happens to the polarization? Well, then the polarization, our 1D polarization, goes to what it was before, minus NE. So this is actually physically correct. And I can kind of explain why we think of it as physically correct, that the polarization, if I only give you a unit cell, from the unit cell is only defined up to addition or subtraction by an integer. We think of the fractional part as meaningful. And the reason why we say that is, suppose I gave you a unit cell and I ask, what polarization do I measure? Well, if I really do a polarization experiment, I go to the surface and I measure the surface charge. And I'm free to add extra electrons. If I want to maintain the periodicity of the system, I should add an integer number of electrons per unit cell. Let me ignore the possibility of fractional particles, but we'll have to come back to that when we talk about fractional TIs and maybe the last lecture. So we interpret this as meaning that polarization, like what would we do to see this? Well, indeed, there is an ambiguity of polarization. Which is charge per an integer times charge per transverse or surface unit cell area, which in 1D this drops out. In 2D it would be a length, and 3D it would be an area. So a general statement is that the odd dimensional, and as I said, polarization, this is the correct formula for polarization in 1D, 2D, or 3D. It starts being meaningful in 1D, so I'm going to think of it as a one-dimensional quantity. The odd dimensional quantities they all have this property. So this is polarization in 1D. They have an ambiguity. And this will be true of the magnetoelectric effect in 3D. That's the new quantity that appears in 3D. We'll see probably next time. In 5D, there'd be another one, I guess. I'm going to focus on 1, 2, 3, 4, I think, for dimensions. So they're not quantized, except if I add symmetry. But what is quantized is their ambiguity. Or maybe a way to put it is they are only defined up to some quantum. Or if you like, only the fractional part is well defined. Fractional part of polarization, that's something with units of E, and the fractional part of magnetoelectric effect is something with units of E squared over H. We'll see later on.
Excuse me?
Yes.
I have another interpretation of your gradient of chi. If we consider it as a gauge transform, that means we choose another reference wave function C tilde. But in this sense, that means our polarization is no longer gauge invariant.
It's not totally gauge invariant, but there's a part of it that I can't change. So suppose I computed this and I got 2/3, 2e over 3. So you might compute it and you might get 5e over 3 or 8e over 3 or whatever. So we would disagree on the total polarization. And that's correct because we could have different crystals with different surfaces and we would measure different polarizations. So in a sense, polarization is not uniquely defined by the unit cell, but the fractional part of polarization is. So for example, if I got 2e over 3, there is no way you would get e over 3. So in other words, we will disagree, but we will only disagree by an integer multiple of this quantum. So I think that's right, that total polarization is not a well-defined quantity if I just give you the unit cell. But the fractional part, or the polarization mod E, that is well-defined.
But in macroscopic things, polarization is unobservable. So in a sense, it should be well-defined. Well,
it's only well-defined once I tell you tell you the surface. So if I just tell you the unit cell, that doesn't tell you how I terminate. And actually, these are good questions because exactly the same thing is going to happen with the magnetoelectric effect and the theta angle. So Chern number, the 2D quantities are different. Those are totally well-defined and fixed by one unit cell. These odd-dimensional quantities, which are in a sense harder, they give some information, but they don't totally determine the physical observable. So what I actually measure is a combination of the fractional part from the unit cell and then this integer ambiguity from how I terminated it. And the same thing will be true for magnetoelectric effect.
So what are the different possible terminations in one dimension?
Suppose I came along. Well, okay, so in 1D, it's like, let's say we had and I cut there, and I just leave it like that, and you cut there, and you add some electron. Maybe you've got a dangling bond or extra molecule that preserves if I'm in higher dimensions, I'd have to worry about preserving the periodicity in the vertical direction. In 1D, I don't. But the point is that you could add an electron there or 5 electrons here or whatever, just depending on, maybe you prepared it in a different gas or different bonding conditions or whatever. But the point is, I'm assuming that you can't add a fractional charge at the surface. Let's assume that I don't subdivide the electron, and then it's well-defined. Yeah.
You mentioned the polarization and magnetoelectric effect, but is it the same thing for magnetization, for example?
Not quite. Magnetization, so magnetoelectric effect is the derivative of magnetization with respect to electric field, or derivative of polarization with respect to magnetic field. Just the magnetoelectric effect before I perturb the system. There is a nice theory of orbital magnetism. It does involve a Berry phase part, but it's not exactly like either one of these. That's actually kind of another possibility. So to be precise, there are two gauge invariant contributions to the orbital magnetization. But I think it's not... So these two... I'm going to show you in a second how these do get quantized by symmetry. As far as I know, orbital magnetization doesn't give you a topological quantized thing in the same way, so I wasn't planning to discuss it. But it is something that has a Berry phase part, but it isn't quite like either one of these. And for one thing, it's kind of intrinsically a 2D quantity.
Okay, so it's not really the... Well, we would think at the magnetic field and electric field as a symmetric point of view, so we have polarization and magnetization, but it's not the same derivation to get the two.
That's right. It is quite different. Orbital magnetization, there's a nice theory worked out along similar lines, but it doesn't wind up being as topological somehow. Let's see, so why is that? I mean, I guess, okay, so by the time I get to 2 dimensions, for example, okay, so I think that relationship, in 3 plus 1D, there's much more symmetry between electric and magnetic fields than there is in lower dimensions. So in 2 dimensions, for example, there are 2 electric fields and 1 magnetic field. And in 1 dimension, there's 1 electric field and no magnetic field. So I think in 3D, there is kind of a duality between them, which shows up in this magnetoelectric effect, but not in lower dimensions. So orbital magnetization, for example, I know that starts to exist in 2D, and you can compute it, and there's a complicated formula for it, but I don't know that it's particularly topological. Find you.
I don't understand something. It seems that the ambiguity in polarization is the number of electrons at the boundary. But from the definition you gave, I understood that this polarization is a bulk quantity defined for an infinite system. So if you don't have different boundary conditions, it should be well defined.
I think not. I think that was kind of the general belief, and people kept trying. So before 1990, people had spent many years computing polarization, and the problem was they would get different answers for different definitions of the unit cell. Like if I drew the unit cell this way, it'd look like, okay, well, this is polarized to the right. Well, what if I drew the unit cell like that? So the truth, the belief now is that polarization, the total macroscopic polarization that I measure, is not uniquely determined by the unit cell. Only the fractional part is determined by the unit cell. So that took a long time to be understood, but now I think everyone agrees on it. At least they've started giving prizes for it. So by some test, people agree on it. Okay, so then finally, so polarization by itself is not quantized. I mean, all kinds of different inversion-breaking crystals have a polarization, but this ambiguity is a clue. Maybe the most non-trivial prediction of this is that with inversion symmetry, and let me start maybe warming up the projector, because I think, okay, I'm not sure I'm even going to get to my slides today. With inversion symmetry, P is quantized. And you'd say, well, of course, because it's 0, that's quantized. But no. To one of 2 possible values. So if you believe in the ambiguity, you have to believe this. And this is an example of how, with the odd dimensional quantities, they're not quantized, they're physical and measurable, but they're not quantized if I don't add a symmetry, but if I do, they are. And here's a simple picture. So our requirement was that P and P plus NE are indistinguishable. One option would be if I've got 0, E, 2E, minus E, minus 2E. So this ladder of values is clearly symmetric under P goes to minus P. So in other words, what I want to ask about is what are the non-trivial fractional, or what are the fractional polarizations that are allowed if I have inversion symmetry, which means that P and minus P should be the same thing. Well, this is one of them, but there's another one, which is the set of half integers. Because this set is also invariant under P goes to minus P. So in the same way, when we talk about the magnetoelectric effect, there are two kinds of time reversal symmetric insulators. There are trivial insulators, which are kind of like this, and there are topological insulators, which in the right language have fractional part of 1/2. The set of half integers and the set of integers are the two allowed cases. I'm just mentioning this as a remark for the future. And then finally, let me maybe close the loop on so getting back to one quick mathematical comment on what the Chern number is.
So, why is P only quantized to two values? How would we determine that?
Well, because suppose you took anything else. Maybe it's easiest to do it operational. If you took anything else, any other ladder of things spaced by an integer. So these are values spaced by integers. Suppose you took minus e over 3. Then you'd have 2e over 3, 5e over 3, 8e over 3. But that's not symmetric under P goes to minus P. So my assumption was that, and this is right, inversion symmetry flips spatial directions. So P is a spatial vector. So inversion symmetry takes P goes to minus P. And if the absolute value of polarization were well defined, then 0 would be the only possibility. But if only the fractional value is well defined, then there is one other possibility. So I guess what I'm claiming is if you took any other ladder spaced by an integer, it wouldn't be symmetric between the above and below. So what are A and F? Okay, so F is let's maybe focus on F. F is a two form. So DA in math language. So the cases that are interesting well, if F, integral of F is non-zero, let me try to give a picture for what does it mean that this is quantized. So the simplest example that I always come back to when I want, what is an example of Chern number? Let me not think about the torus, let me think about the sphere. And this H equal to minus n dot S, that gives me a Berry F that's like a magnetic monopole. So the Berry F is always directed outward. Let's say outward. So this is a two form, and the interesting case, which you probably know from hearing about magnetic monopoles and Dirac strings and all that, is that if I have this case where F is all outward, then I can certainly find a local patch where there are wave functions, let's say spinors, so that if I take A from the wave functions, then F is indeed dA. So F is locally exact. In other words, locally, it is the derivative of a one form. As a consequence of that, that means that it's closed. In other words, if I take dF, I get 0. But in this monopole case, when the integral of F is non-zero, F is not globally exact. In other words, there is no global definition of chi that's smooth everywhere that will give me F equal to dA. So it's not globally exact, or in general, it's not really exact. So in other words, in cases where F integrates to something non-zero, and you can check if you want, play around with your usual definition of spinors, and you'll find out that there's a so-called Dirac string passing through a point on the sphere where the spinor is not well defined. So if you try to define wave functions or vector potentials on the monopole, you run into a bit of trouble, as I kind of sketched last time. So F is therefore an element of the second cohomology group. And to be more precise, there's one ingredient that we have to add, and this lets me give an answer to a question that I was unwilling to answer yesterday, at least a partial answer, which is the following. So what is the Chern number to a mathematician? Well, it's the integral of f. F is, in this case, the first Chern form. An element, since it's a 2 form, it's an element of H2, which is the second cohomology class, of my manifold, in this case, the sphere, let's say in general M. And there's one subtlety, which is the following. When I was just thinking about differential forms and not about having them come from normalized wave functions, so what I talked about last time was just differential forms. And then it's natural to think about cohomology with real coefficients. Here we have an additional constraint, which is that, in a sense, the differential forms we were talking about before were not quantized. I could multiply them by an arbitrary number, while where we get quantization, so for example, the Dirac string, the monopole flux is quantized because this is coming from normalized wave functions. That's why I only get integers for the Chern number. If I were allowed to divide my wave functions by 2 or 3 or something, then clearly I would get non-integer values of f. So the fact that I can't do that is how the precise kind of cohomology that comes up when you're dealing with, in a sense, quantized things, or things that come from normalized wave functions, is cohomology with integer coefficients. And this is actually what's related to homotopy groups, as it turns out. And if you want a proper definition of this, well, you first define homology with integer coefficients and then take the dual. But this is very close to what we did before. It's, in a sense, it's still differential forms that are closed but not exact, but there is a notion of quantization which winds up that I can add integer copies, but I can't add fractional copies of chains or paths. So then, in general, there are Chern forms in even dimensions. And in fact, there's a sense in which for line bundles, if I'm just thinking about the abelian case, it turns out Chern number is in a sense complete. And maybe we'll do that, some calculation next time. H2k of mz. And there are Chern-Simons forms in one dimension less. A way to sort of understand the relation between Chern-Simons forms and Chern's forms physically is to think about polarization in the Hall effect. So this is actually how Thouless got the polarization formula. He thought, well, I've got my one-dimensional system, and I think of changing some parameter of the system in a periodic way. Then by the time the parameter gets back to where I started, I must have pumped an integer number of charges. In other words, I must have changed the polarization by an integer, and I could sort of track which integer as I went along. So that was his argument, that integral of change in polarization with respect to some parameter d lambda, this is quantized. And to get the Chern formula, you basically take the parameter to be ky if I had defined the polarization using kx. So maybe I'll say a bit more about that. But there's a close relation between the Chern forms in even dimensions and these polarization-like quantities in odd dimensions. And the relation is, those are called Chern-Simons forms. They're just the objects whose differential is the Chern form. So for example, dA is f, the first Chern, and the second is that d of something called k, which is basically af plus aaa, is f wedge f, which is the second Chern form. That's the four-dimensional object. So as a non-trivial thing you probably haven't heard before, if I'm in 4 dimensions, if you give me a 4-dimensional band structure, there's an object just like Chern number, quantized to be an integer, which is integral of Fij Fkl. That's the 4-dimensional integer Hall effect. So that's a clue from this existence of another Chern form. Okay, so I think that is enough math for now. Let's take a little break and you can relax and look at some pretty pictures. If I can get the projector going for 15 minutes. So questions while I set this up would be nice.
Yeah, so I have a question. So for these Chern-Simons forms, you've been emphasizing the odd dimension, but thinking about polarization, odd and even dimensions don't seem different from each other.
Basically, the dimension where it starts to be well-defined is odd. Once it's defined in one dimension, I can always use it in higher dimensions. It basically, I should say, exists in one dimension or higher would be the best way to say it. So it's fundamentally a 1D quantity. So, for example, the magnetoelectric effect, which is related to the 3-dimensional object whose derivative is 4D. So I guess what do I mean by a 1-dimensional object? I mean it's of one form. If you like, it's something with one k derivative. So when I integrate it dk in higher dimensions, I'll get factors of area, which is a clue that it can't be that universal. In the same sense, magnetoelectric effect is a 3 form. It's got 3 dks. So it can give me something dimensionless in 3D, but in any other dimension it won't be dimensionless. So if you like, there's the dimension where it starts, I get a dimensionless quantity, which gives it some hope of being topological. In higher dimensions, it's still physical and all that, but not necessarily. It can't be universal. Okay, replace the bulb. I know French. So, okay, so I think I already told you about Gauss-Bonnet. So let me just quickly flash through and summarize the things we said. So we've got a vector potential living in parameter space, in case my handwriting wasn't clear enough. And that, for the U1 case, it has a U1 gauge transformation just like the vector potential in dynamics. And there's a plus here because I think I had minus I up above instead of plus I. That plus is not significant. So the first physical observation related to this was here. This is just writing out what I said before, which is that if I give you a band and I integrate the curl of A, I get F. And when I integrate F, I get an integer. That integer just tells me how much does that band contribute to the quantum Hall effect. So far we haven't imposed any additional symmetries and all that. Haven't gotten to Z2 yet, I'm afraid, but I promise we will next time. Now, another thing I haven't talked about that I should, but I'm going to do it when I talk about topological responses, is at least for the integer quantum Hall effect, the one we've talked about so far, there has to be an edge state. So in other words, so far we've been talking about insulators. There's an argument of Laughlin that I would like to go through when I have a bit more time, saying that what distinguishes the quantum Hall state from an ordinary insulator is really, there's a so-called anomaly. There have to be gapless degrees of freedom. And to be precise, there have to be chiral degrees of freedom such that the number of right movers minus the number of left movers is an integer, which tells me which quantum Hall state I'm in. In the simplest case, I don't have any left movers, say. I've only got right movers. And the number of right movers is just determined by the bulk quantum Hall. So this is saying something in the bulk where the system is gap is telling me about what happens at the gapless surface. So we ought to be able to justify that. And in fact, I might not, if I don't get to the Laughlin argument, that's okay, because what I really want to do is show how this is a property of Chern-Simons field theories, the same kind of field theory that Xiaogang wrote down. There's a very beautiful connection between the bulk Chern-Simons theory and the gapless edge chiral fermion or chiral boson. So this is a more hand-wavy picture of why there's an edge, but you all are, future stars. You deserve better. So we'll do it a little bit better. Okay, so now what we're going to get to is the following idea. So let me sketch it. You might ask, well, you've probably learned about the integer quantum Hall effect in a way where all this topological invariant stuff was kind of hidden. The integer quantum Hall effect and Landau levels and all that, you can get, if you want to understand how would that show up in this formalism, if you take the Hofstadter model and let the flux get smaller and smaller, the energy levels get flatter and flatter and basically just become the Landau levels. So there is a sense in which each Landau level in the continuum has Chern number 1. That's why when I fill up that Landau level, I get an extra Hall quantum. So why would you want to work on a lattice, given that most experiments on the quantum Hall effect are in a very low-density system where the continuum limit is okay? Well, it's because when we think about spin orbit, which is what drives topological insulators, then that's not small. It's actually much more appropriate to think about a crystal and to think about significant amplitudes within the unit cell. And it's also naturally commensurate. Unlike an applied magnetic field, there's no real reason for it to be commensurate with the unit cell. While the spin orbit is a property of the crystal itself, it's automatically commensurate. So the simplest case, and maybe I'll get to one example of a Hamiltonian and then stop. So at an abstract level, here's what the quantum spin Hall effect is, if I don't worry too much about the topology. So we've done integer quantum Hall. Think about L dot S. So that's the spin orbit you learn about in undergrad physics. If I fix the spin to be up, this is a momentum-dependent force. A momentum-dependent force is like a magnetic field. So this is kind of like a magnetic field that points one way for spin up and the other way for spin down. And that suggests that if I chose the right Hamiltonian, I might get a system that's in a quantum Hall state one way for spin up and the other way for spin down. And the fact that these two are symmetric reflects something, which is actually why spin orbit is so ubiquitous. Spin orbit is consistent with time reversal. So both L and S flip under time reversal. A magnetic field breaks time reversal, so you only get it in some materials that at some point broke time reversal symmetry. Spin orbit is there in basically every material. So maybe you should look at what topological phases might be driven by spin orbit coupling, and those are the topological insulators. And they're related to Berry phases also, so we need to explain that. But first, the reason why one needed to find a new kind of topological invariant was basically the following. I think most of us thought before 2005 that if you made this can't be very topological, we thought, because if you look here, it looks like this is a one-dimensional wire with modes going in both directions. We know about localization. We know if we add disorder, that will localize. End of story. There's no longer a protected edge mode. It can't be topological in the same way. It was called quantum spin Hall effect originally, but that's not really quantized either. So even if you could make this, it looks so far just like two copies of the integer quantum Hall effect. Well, the problem, if you like, in more mathematical language, was that all the Chern numbers have to be 0 by time reversal invariance. That's kind of logical because sigma xy breaks time reversal. So if I have something that determines sigma xy and I know sigma xy is 0, then the topological something had better be 0 also. So we didn't know anything that could topologically protect this until some work of Kane and Mali around 2005, and that kind of kicked off a lot of new developments. What they showed is that there's another kind of topological invariant which is very similar in some ways. You can think of it as a parity, something that's odd or even, or a Z2 invariant. So we have to understand, why does time reversal, and specifically time reversal acting on fermions, give us Z2 topological invariant quantities? And what are the physical properties of those 2D topological insulators? So I will say a little bit more and then go back to the blackboard for the last 5 minutes to kind of make some topological statements. So let me show you just one Hamiltonian for a 2D topological insulator and then get back to a bit of math. So this was one of the two Kane and Mali papers from 2005, was the following idea, and it's pretty elegant. So I want to take a model where a little bit of spin-orbit coupling will put it in a topological phase. And a nice place to start is Dirac fermions, like graphene, because that's a semimetal, so it's very sensitive to perturbations. So let's take the honeycomb lattice, and one perturbation I could add, so this is just spin-independent hopping on the honeycomb lattice, this would give me Dirac nodes. This is basically graphene. If I went from graphene to boron nitride or something else, where the two atoms in the unit cell are different, let's say, just different on-site potentials, then I will open up a gap, and that's a very boring system that's an ordinary band insulator. So I want to try to find a different kind of insulator. And what they did was use some work of Haldane to start with. So the first term they wrote down, they basically added an SZ to an old model of Haldane, where Vij is the following. So this is second neighbor hopping, and Vij is related to the cross product of the two vectors that I hop along, where D1 and D2 are drawn, if you can see the small writing here, for example. So I've got second neighbor hopping terms with some phase in them. And this is basically kind of like a magnetic field. It breaks time reversal. It turns out that there is a sense in which the flux is zero, but it still breaks time reversal. And if I didn't have this, if I had spinless fermions on the honeycomb lattice, and I added this term of Haldane's, he wrote that down as a simple model of a Chern insulator, a quantum Hall state on the lattice. Kane and Malik came along and said, well, I'm going to make two copies of that with SZ. So if they just wrote this down, it would be like what I did before, making two copies of the quantum Hall effect, and we wouldn't have cared very much. But then they said, well, I'm going to add a term that breaks SZ conservation. So if you like, this term is a bit artificial because SZ still commutes with the Hamiltonian. It's like I've got up electrons and down electrons, and they don't talk to each other. That's not the way real electrons work in solids. Spin is a vector. The components don't commute. So I should add something like this. And probably many people would have thought that if I add this, nothing is quantized anymore. But they showed that it is actually stable to adding this kind of spin-orbit coupling, so-called Rashba spin-orbit coupling. But it's stable because of this new Z2 kind of invariant. So that's where we'll pick up next time. So to make one last couple of mathematical statements, let me say, if I want to think about Chern number for many bands... yes.
How important was it, the assumption that they made that this term, the lambda is of, preserves all the symmetries of the lattice? Like, if I had, could I suggest a different term that respects time reversal and could lead to the transition of graphene to a topological phase, or is this a unique term?
It's not too unique, and I can add a little bit of disorder. So I guess I'd put it this way. Suppose I add a large lambda S0. That opens a gap. So I've got a gapped phase where the bottom two bands, it turns out that Z2 invariants are associated with pairs of bands. This is a 4-band model. The bottom two bands have a non-trivial Z2 invariant. I start to perturb the thing with anything almost, anything that respects time reversal. So I could change the lattice by a little bit. I could add fluctuations in the graphene atoms or whatever, as long as I preserve time reversal. The way you can tell this as time reversal is that it does have an I, which would break time reversal, but that multiplies SZ, which is also time reversal odd. So anyway, once I've got the gapped phase, any small perturbation that respects time reversal won't change the phase. That would be kind of the statement. So, but there's no guarantee. If I think about all the possible perturbations to graphene, some of them will put me in, if they break time reversal, they usually put me in an ordinary quantum Hall phase. If they don't break time reversal, this will give me an ordinary insulator. This will give me a topological insulator. If I have both of them, they'll kind of compete. I could get a metal. Nothing prevents that. So what exactly happens with various perturbations, it's hard to say anything too universal. But the one thing I can say is, if this is the strongest and everything else, so this is stable to any small perturbation except for breaking time reversal. So it's topologically protected as long as I still have time reversal.
But the second term is the Rashba term.
Yes.
And that one preserves time reversal.
Exactly. So, for example, what they showed was that if you have this and then you add a little bit of this, it's stable. It still remains in the topological phase. When maybe, if we didn't know about the topological invariant, we would have thought that it wasn't stable to Rashba. But if I added instead, if I had sort of Rashba dominated instead of that, then in general I won't be in the topological phase. I'll actually be in a metal.
But you don't need to break inversion symmetry, right?
Right. You don't need to break inversion. The lattice is almost kind of irrelevant.
Oh, really? I thought you only get spin orbit when you do break inversion.
You only get Rashba when you break inversion. Rashba, to be precise, comes from spin orbit. It's a spin orbit term that's usually related to Z-directed inversion breaking. Like if I've put my graphene on a surface. But in general, there are some spin-orbit terms that break inversion and some that don't. And I don't think there's a strong correlation between which ones are topological and which are not.
Because even like the first term, right, that's in next nearest neighbor model, and
Yeah.
that one does break inversion as well.
I'm not sure about this particular model, but I know that there are inversion symmetric models like the diamond lattice in 3D. I can make a topological insulator out of that is inversion symmetric. I suspect that this does have inversion, but anyway. Yeah, I think it does have inversion. Okay, so let me just say a little bit to kind of summarize what Chern numbers are more methodically. So this integer cohomology, that is the one that is related somewhat more closely to homotopy. So before, for example, when I did H1 over the reals of the sphere, actually I did the circle, this was R. But if I did it over the integers, it turns out that is the integers. And in general, there's a famous theorem due to the great Polish topologist. We can say the following thing. For a space, if pi k is 0 for k equals 0, trivial, up to n minus 1, which means the space is n minus 1 connected, then at least for some of the pi's, for sufficiently small pi, basically pi's up to n, so pi n, well, okay, the previous ones we said are trivial. For pi n is equal to the, to be precise, the abelian part, but that only matters for n equal to 1. For n higher than 1, sorry, let me stay at the right. What I want to say is that the nth cohomology group over the integers is almost the same as the nth homotopy group, where almost the same means the same if n is greater than 1, and if n is equal to 1, if n is greater than 1, these are both abelian and they're both the same. If n is equal to 1, then this might be non-abelian, and this is the so-called abelianization. So it's the integer cohomology groups that can be specifically related to homotopy groups, and that's useful because what was shown by Avron, Seiler, and Simon in a nice... So they kind of made what Fowlis et al. Did a little bit more precise. They said basically that the pi n, let's focus on pi 2. So first they said that they gave a more rigorous argument that T2 is like S2 for the purposes of Chern numbers, so pi 2 is good enough, and this is a 1983 PRL. That pi 2 of m sub n cross n, where m sub n cross n equals non-degenerate, and that's crucial, n by n Hamiltonians. So you could think of these as band structures. Two-dimensional band structures, once I've used their argument that pi 2 is enough. Two-dimensional band structures where bands don't touch. That this is equal to n minus 1 copies of the integers, which is basically the statement that every one of the n bands has a Chern number, and all the Chern numbers sum up to 0. And then the corresponding fact, so there's a proof. I actually have it written out in my notes, but I'm not going to go through it in class. It's not that hard. It uses one fancy math result, which maybe I'll write up for your general knowledge, called the exact sequence of a fibration. But otherwise, if you're willing to believe that, the rest of the proof is easy. The corresponding statement for topological insulators, which is what we worked on, is if I have time reversal, then you can view it as if I've got, so now I've got two n bands. I want to take pairs of bands. Again, there's a sum rule, so I can just write this as n minus 1. There are n minus 1 Z2 invariants for a 2n band system. So to be precise, maybe we'll start with next time is explaining why time reversal of fermions forces bands to be degenerate at some points. It doesn't do that for bosons. Anyway, once I've got time reversal, bands come in pairs, so any topological invariant should be a property of the pair, and every pair has one Z2 invariant, and they have to add up to 0, where adding in Z2 means like odd plus odd is even plus even is even, odd plus even is odd. So for your mathematical knowledge, there's one powerful trick. As I said, homotopy in general is kind of hard, but what a lot of calculations, both for topological defects and this calculation use, is called the exact sequence of a fibration. It's not actually in Nakahara, but it is in Mermin. At least I don't think it's in Nakahara. Exact sequence means I've got a series of maps where the image of this one, in other words, the points here that came from this is the kernel of this one. And there is an exact sequence of homotopy groups, which is something like pi n of H, pi n of G, pi n of G mod H, pi n minus 1 of H, and so on, with 3 objects per n. It's called the long exact sequence because in principle it includes all the homotopy groups you could want. So what they basically did was figure out a way to pose the Chern problem as calculating something like pi 2 of some complicated set G mod H, but if they know the results for G and they know the results for H, then this is a trick to kind of work out maybe G divided by H. So if you want to learn maybe one somewhat sophisticated topology trick that's actually useful in physics, Mermin gives kind of a physicist derivation of this long exact sequence, which is somewhat handy for hard homotopy groups. So that's my last mathematical comment. So anyway, so we've more or less said, I think, what we're going to say about the integer case. And if you want a little bit of motivation for topological insulators, aside from the fact that they exist experimentally and they have various neat properties, motivation 1 would be that these Z2 invariants are actually related to the non-abelian Berry phase and to the magnetoelectric effect. And motivation 2 would be that when we think about the responses, in the same way that polarization is a little bit related to the integer quantum Hall effect, the magnetoelectric effect is really what kind of physically is quantized. So actually, let me give, sorry, I suppose I see the organizer standing, so sorry, I have to stop there, and I will also explain to you the following mysterious table, at least a little bit. So that's motivation to show up next time. I think I'd better stop. Thank you.